So good evening all. So in organic chemistry, in your last class we introduced what is GOC, general organic chemistry. Basic introduction we discussed what is hybridization, how to determine hybridization for variable organic molecules we discussed. So if you want to calculate hybridization of any molecule, only one key point is you need to identify, that is how many number of sigma bonds plus number of lone pairs. Sum of sigma bonds is equal to one number. If that number is 2, sp. If it is 3, sp3. 4, sp3. If it is 5, sp3d, like that. Okay. So every time only one point you need to remember. If any lone pair is involving in delocalization, that lone pair never involve in hybridization. If it is a localized lone pair, try to involve in hybridization. If it is a delocalized, simply ignore it. Clear? So next. So we are going to show you how to make overlap between two atoms, later on how to calculate hybridization for inorganic molecule and some applications. Okay, so take this molecule CH3 and here this is CH3. So what is the name of this molecule? Is it ethane or not? It is ethane. So what is the hybridization of two carbons in this one? Is it sp3 or not? Yes, it is sp3. Ethane sp3 will be the hybridization. See, if I take carbon in their excited state, how to write configuration? 1s2, 2s2, 2p2 or not? Is it right? Now what about ground state? This is s orbital and this is p orbital. Here two electrons are there. This is 2 and this is 2. Is it ground state or not? So I don't want to write every time, just you concentrate here. Now if I write excited state, then see, this one of the electron undergo excitation and it will give 3 electrons in this orbital, right? This electron undergo excited here and you will get 4 electrons. Now how many free electrons? 4. Now one s orbital and 3 p orbitals are intermixing. This is s orbital, px, py, pz. One s orbital, 3 p orbitals are mixing for one carbon. This carbon hybridization is what? sp3. This carbon? sp3. So in this carbon 4 atomic orbitals are overlapping. I am intermixing 4 atomic orbitals. So if I intermix 4 atomic orbitals, you will get like this. See, this is one hybrid orbital, this is second hybrid orbital, third hybrid orbital, and this is fourth hybrid orbital. How many sp3s are present here? 4 sp3. 4 atomic orbitals I am combining and I am creating 4 sp3. How many electrons are present? 4 electrons. Here 1 electron, 1, 1 and this is 1. Right? And what is this? Is it atomic orbital or hybrid orbital? Hybrid orbital. This 4 I am mixing, I am converting into similar and equal energy hybrid orbitals. If I intermix this 4. If I mix this 4, 1 s orbital, 3 p orbital. Then what you will get? 4 sp3. Is it clear? So now this is first sp3, second sp3, third sp3 and what is one more? Fourth sp3. This is for first carbon. Can I repeat same process for second carbon? Second carbon also having how many hybrid orbitals? 4 hybrid orbitals. So this is a first hybrid orbital. It is overlapping with this carbon. This is second hybrid orbital, third hybrid orbital and this is fourth hybrid orbital. Right? So this carbon also carry 4 electrons or not? This is 1 electron, 2, 3, 4. Then what is this? sp3. And here see sp3, sp3 and here also sp3. Is it right? See, when carbon undergo excited state, you will get 4 atomic orbitals. 1 s orbital, it is outer shell or not? This is 1s and what about this one? 2s, 2p. 2s, 2p I am taking. I am taking only 2s, 2p. I am not taking 1s. Because outer electrons are valence electrons. Only 2s, 2p I am taking. 2s carry how many electrons? 2 electrons. 2p carry 2 electrons. This is ground state. If this electron undergo excited state, that becomes 4 electrons. How many 4 orbitals are present? 1 s orbital and what is one more? 3 p orbitals or not? So when one s orbital, 3 p orbital combine together, then what you'll get? 4, 1 plus 3, 4. Yes, p3. Yes, p3. Total how many? 4 sp3. 1, 2, 3, 4. And here also this carbon, 1, 2, 3, 4. So this carbon is this one. This carry how many hydrogens? 3 hydrogens. Every hydrogen carry 1 electron. Every hydrogen carry 1 electron. Here also same. Here also same. Okay. So there is a overlap between these two. So what kind of overlap between two carbons? What is the kind of overlap? sp3, sp3. And what about carbon hydrogen? sp3s. Total how many sp3, sp3? 1 sp3, sp3. How many sp3s? 6 sp3s. 1, 2, 3. Here one more hydrogen or not? Total. 6 hydrogens are there or not? 3 plus 3, how many hydrogens? 6. Here 6 hydrogens, 6 carbon hydrogen overlaps. Carbon hydrogen overlaps. Total how many different overlaps are there? Total how many different overlaps? Only 2 different overlaps. sp3, sp3. What is one more? sp3s. Total number of overlaps are how many? 7. So based on this, it is clear that whether any atomic orbital is combining or not combining. Okay, just listen, don't write. So after that you take down. If I take ethene, so what is the hybridization of this carbon? Ethene. What is the hybridization of this carbon? sp2, sp2. Hybridization of this carbon is sp2. So if I take carbon in their excited state, 1 electron, 1, 2, 3, 1, 2, 3. So is it excited state or not? This carbon hybridization is sp2 and this carbon also hybridization is sp2. This one as well as this one sp2. Now how many atomic orbitals I am combining? I am combining s orbital, px, py, but not pz. Pz is there, I am not overlapping pz. I am combining s, px, py, any two p orbitals. It may be px, py, px, pz, py, pz, any two. But I am not overlapping one atomic orbital. So is this orbital is overlapping? Is this orbital I am mixing? No. I am mixing how many? 1 s orbital, 2 p orbital. But here in this case, 1 s orbital, 3 p orbitals I am mixing. Now in this case what happens, see, whichever orbital is not mixing, that is called real orbital. This point you need to remember. Real orbital, also called pure orbital. So it is also called unhybrid orbital. Okay, real, pure and unhybrid orbital. Clear? So for this carbon, how many unhybrid orbitals are there? 1. And this carbon? 1. Total how many unhybrid orbitals? 2. So I can say like this, see, this is a carbon, first hybrid orbital, second hybrid orbital, third hybrid orbital. Total how many? 1, 2, 3. So I can say 3 sp2. Okay. So how many unhybrid orbitals? 1. So this is called unhybrid orbital. pz, not overlapping. Now 1, 2, 3. Here 1, 2, 3 and it is not overlapping. It is unhybrid. So what is this orbital? pz. What is this? sp2. Here sp2 and what is this? sp2. Right? Total how many electrons? 4. But these 3 electrons are belongs to sp2, 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 but this is belongs to pz. Now can I repeat for second carbon? If I repeat for second carbon, you can get like this. This is 1, this is 2 and this is 3. So this is this is 1, this is 2 and this is 3. And this is unhybrid orbital pz. So 1 electron, 1 electron, 1 electron. So this is sp2, here sp2 and here also sp2. Right? Now here how many hydrogens are present? 1 hydrogen, here 1 hydrogen. This side 2 hydrogens, this side also 2 hydrogens. Right? Now what kind of overlap is observed here? Between two carbons, what is the kind of overlap? Is it a sigma bond? This is sigma. What about above? Pi. Is there any pi bond here? No. Here one more electron is present. Now one more overlap. What is the kind of overlap? sp2, Yes, overlap is there or not? sp2s, 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 sp2s. Then what happens? See, what about these two orbitals? Is this two are unhybrid or hybrid orbitals? Unhybrid. These unhybrid orbitals undergo sidewise overlap. So whenever if they undergo sidewise overlap always give pi bond. Half pi bond above, half pi bond below. This carbon carry any unhybrid orbitals? Any unhybrid orbital is there or not? Yes, one unhybrid orbital. And here also one unhybrid orbital. In this carbon, no unhybrid orbital. That's why no pi bond. But here see, one unhybrid orbital is there. Unhybrid orbital, also called real orbital, pure orbital. That pure orbital undergoes sidewise overlap. Always, whichever orbitals are not mixing, if they undergo sidewise overlap, that orbitals are responsible to give pi bond. So how many sp2 sp2? 1 sp2 sp2. How many sp2s? 4. 1 2 3 4. So this carbon carry 2 hydrogens, here also 2. Total 4. 4 sp2s. Okay. So actually carbon should carry sp3. If they carry sp2, one unhybrid orbital, also called pure orbital. So it should carry sp3, but one is not involving. That is called real orbital, pure. Whichever is intermixing, they are called hybrid orbitals. So these three responsible to give 3 sp2, 3 hybrid orbitals, 1 unhybrid orbital. So this carbon unhybrid orbital, this carbon unhybrid orbital responsible to give double bond. So this is not 2 double bonds, half pi bond above, half pi bond below. So this is a sigma bond, and what is this? Pi bond. So that is actual overlap between 2 carbons. Right, take down. So try to write sidewise overlaps and head-on overlaps. What type of overlaps you try to remember. So which orbitals are responsible to give sigma bond? Sigma bond is produced by head-on overlap. Hybrid orbitals produce sigma bond. Unhybrid orbitals produce pi bond. Whichever orbitals are not intermixing, if that orbitals are overlap in a sidewise manner between two adjacent carbons, they are responsible to give pi bond. Next. So go through triple bond. This is called ethane. Ethane, what is hybridization? sp. Triple bonded carbon. It is ethene, and this is ethane. Ethane. So here also same. Carbon, I am writing excited state directly. So one electron in s orbital, remaining 3 electrons on p orbital. Now I am intermixing one s orbital and one p orbital only. This is px, py, pz. So I am not intermixing these two. How many real orbitals? 2 real orbitals for one carbon. 2 carbons, 4 real orbitals. So first, if I intermix this s orbital, p orbital, then what you will get? One s orbital, one p orbital. Then what you will get? 2 sp. This p may be any one. It may be px, py, pz. Don't think that always s combined with x only. S may be intermixed with y or z or p, x, any one. Any one of the p orbital, this s orbital is going to be intermixed. So now how many sp? 2 sp. So this is first sp, second sp. This is 1 sp, here second sp. How many electrons here? 2. Add 2 electrons. Right? And how many unhybrid orbitals? 2. So this is py, and this is one more. What is this? Pz. What is this? Py. And this is pz. Here one electron, here one electron. Right? This carbon carry one hydrogen or not? So this side I would like to write hydrogen. So between this carbon one overlap is there. Can I repeat this carbon? So this carbon also having one sp, and here also one more sp. Here this is py, and this is pz. Py, pz. Second carbon I am repeating. Here also 2 electrons are there. This is sp, and here also sp. Right? It is also overlapping with hydrogen. And here 1 electron or not? Now see, this pz overlap with this pz. This py overlap with this py. And here also same. This py overlap with this py. This pz overlap with this pz. This is y and this is z. So z to z like this. So here half pi bond and here also half pi bond above. Half pi bond below, half pi bond below, like. So total, what is the kind of overlap? SP overlap or not? How many SP? 1. So then how many SPS overlaps are available? 2. 2 SPS. SPS total 2. So how many real orbitals are present in ethene? Ethene carry carbon 2. But here it carry 4. 4 responsible to give 2 pi bonds. So this is sigma bond. How many pi bonds are there? 2 pi bonds. That is the answer. So when sp hybridization is present on any carbon, remember they carry 2 real orbitals. If they carry sp2, 1 real orbital. If they carry sp3, no real orbital. Why I am focusing on real orbitals? Because always real orbitals will undergo sideways overlap. Always sideways overlap responsible to give pi bond. This is sideways overlap, this is head-on overlap. Head-on overlap always give sigma, sideways overlap always give pi. But both are covalent bonds only. Don't think that sigma bond is covalent, pi is not a covalent. Both are covalent bonds. This is head-on covalent, side-on covalent. Side-on covalent nothing but pi bond. So this electron keep on delocalizing above the plane and below the plane like this. It is keep on delocalizing. So on that time sideways overlap above half pi bond, below half pi bond. Total how many pi bonds here? 1 pi bond. Here 2 pi bonds. So I can say that sp, if this carbon carry sp means 2 unhybrid orbitals. Here also 2. Total 4 unhybrid orbitals. So 2 pi bonds carry 4 unhybrid orbitals. Clear? So try to remember 2 points. Hybrid orbital and unhybrid orbital. Hybrid orbitals always responsible to give sigma bond. Unhybrid orbital also called pure orbital or real orbital. This unhybrid pure real orbitals responsible to give pi bond. That's it. This is called propadiene, also called alene. Propadiene, alene. So what is the hybridization of this carbon? sp2. What about this? sp. And here sp2. How to calculate hybridations? Yesterday I given. In last class already explained how to calculate hybridization. Only count sigma bonds. Around this carbon how many sigma bonds are there? 3 sigma bonds. And here 2 sigma bonds. And here 3 sigma bonds. 3 sigma bonds means sp2. 2 sigma bonds means sp. Okay. So this carbon carry how many unhybrid orbitals? This carbon carry how many unhybrid orbitals? 1. Here 2. And here 1. So this is your first carbon. First carbon hybrid orbital. Here second hybrid orbital. Third hybrid orbital. This is middle carbon. Middle carbon sp. sp, sp. Now this is third carbon. First hybrid orbital. Second hybrid. Third hybrid orbital. Here 2 electrons. Here 1 electron, 1 electron. And here also 2 electron, 1 electron, 1 electron. Right? So what is this? sp2, sp2, and here also sp2. And what is this? Is it sp of middle carbon or not? This carbon sp. Right side also sp. And what is this? sp2, and here also sp2, and here sp2. And see, this carbon carry one unhybrid orbital. What is that? py. Right? 1 electron. This carbon also carry one unhybrid orbital. That should be pz. It should not be py. Okay. So this carbon carry how many unhybrid orbitals? 2. So this is py, and see this is pz. So these two carry 1 electron. This is py, pz. So this py will overlap together. Py overlap. And here also py overlap. Okay. Then this pz overlap together. This is pz. So pz sideways overlap. This pz sideways overlap. So I can say one thing. Here one sigma bond is present between two carbons or not? This carbon, sigma bond. This carbon, one more sigma bond. Right? This carbon carry how many hydrogens? 2 hydrogens. And here also same. 2 hydrogens, and here 2 hydrogens. So I can say this carbon having 2 hydrogens, and here also 2 hydrogens. Is there any pi bond here? Between these two here, above half pi bond, below half pi bond. So I can say here one pi bond. And here also one pi bond. But what happens, see, this pi bond is formed by, so pi, py overlap. And this pi bond is formed by pi, pz overlap. So I can say that py and pz overlaps exactly perpendicular to each other. Right? X-axis, y-axis, z-axis, how they are? Perpendicular to each other or not? So I can say that this pi bond and this pi bond not in one plane. They looks like this. This is vertical and this other pi bond is horizontal. So I can say this is vertical and this is horizontal. So overall we can write this structure like this. See, this is carbon vertical, this carbon horizontal, this is thick line, this is dotted line. Here carbon hydrogen and here hydrogen, hydrogen. So that's why alene, 2 double bonds not lie in one plane. 2 double bonds are not vertical, 2 not horizontal. They should not be like this. They should not be vertical. One pi bond is vertical, other pi bond is horizontal. Because here px overlap or py overlap. Otherwise py, pz. Otherwise pz. Okay. So that's why on this particular carbon, y and this is y. Here z and this is z. Okay. These two orbitals never overlap with same plane. Because one particular orbital cannot carry yy. Suppose if this orbital if you take, either it is xy or it may be xz or yz, anything is possible. Only two are possible. Suppose if both are xx possible here, px possible? No. Suppose if both are px, it may be vertical. One carbon never give two px unhybrid orbitals. It may be px, py, pz, any different axis. Okay, suppose if I take three different axes here now. So this is Py, here Pz, and this is Px. Now next case, if I take one more carbon, suppose if it is Px should overlap because both are in same axis. Px never overlap with Py because both are perpendicular. In order to overlap, they should be in one plane. That's why Py one more overlap, Pz one more overlap. So how many unhybrid orbitals are present? In this one, how many unhybrid orbitals? 4. 2, 3, 4. So what type of carbon overlaps are present? sp2s overlap is present or not? How many? sp2 sp overlap. How many sp2 sp overlaps are present? Only sigma we need to consider. Don't consider pi. Only sigma bond. Without sigma, can you write pi bond? Without sigma, can you write pi bond? No. Without pi, can you write sigma bond? Yes. That's why consider only sigma bond while writing overlap. Okay. So this carbon overlapping with this carbon or not? Is this carbon overlapping with this carbon? So this carbon, what is the hybridization? sp2. This carbon, what is the hybridization? sp. Now what is the overlap? sp2 sp. Then what about this two? sp2 sp. So how many sp2 sp? 2 sp2 sp. Any other overlaps? sp2s is possible? How many? 4. That is the answer. These are the variable overlaps. Total number of overlaps are 6. Total 6 overlaps in which 2 different overlaps are present. That is the case. So what is the name of this molecule? Propadiene. Propadiene. Molecule name is propadiene. Otherwise you can say alene. Common name is alene. IPAC name is propadiene. So take one question. Which of the following hybridization not exist for carbon? Which hybridization is not exist for carbon? sp3, sp2, sp, sp3d. Which is not exist for carbon? Which hybridization is not exist for carbon? sp3d. Why? What is the reason? Why it is not possible? Due to absence of d orbital. Carbon not have any d orbital, that's why sp3d is not possible. Which of the following hybridization not exist for carbon? That is sp3d. Dash orbital overlap produce pi bond. Dash orbital overlap produce pi bond. So that is hybrid orbital B. Unhybrid orbital option C. Non-bonding orbital option D, none. Which orbital overlap produce pi bond? Which one? That is unhybrid. Unhybrid also called pure orbital, also called real orbital. See, the number of unhybrid orbitals present in ethene and ethane are the number of unhybrid orbitals present in ethene and ethane are 2 4 4 comma 4 4 comma 2 2 comma 2. Ethene and ethane. Ethene means double bond. What about ethane? Ethane means triple bond. It is a double bond, and what is this? Triple bond. Ethane is triple bond. The number of unhybrid orbitals present in ethene and ethane are 2 comma 4 or 4 comma 2 or 2 comma 2. 2 comma 4. 2 comma 4. Ethene carry 2, ethane carry 4. Next, The number of real orbitals in propadiene is propadiene or how many real orbitals are present in propadiene? That is 4, 6, 2, option D 8. Propadiene. How many real orbitals present in propadiene? How many? That is 4. Just now given propadiene. Alene also called propadiene. The type of pi bonds present in propadiene are. The type of pi bonds present in propadiene are. Option A 2, 2 py 2 pz py px. Option D none. What type of pi bonds present in propadiene? 2 pi bonds are in same plane? No. Remember, 2 pi bonds never exist in same plane. Okay, even sigma bond, pi bond, even one more pi bond. Sigma bond is in x-axis, first pi bond is in y-axis, other pi bond is in z-axis, like that. 3 are not in one plane. Okay, so looks like one plane, but actually they are not in one plane. So answer is what? 2 pi bonds are different. So don't think that only px overlap is sigma bond. When px forms sigma bond, pz forms pi bond. If py forms sigma bond, pz forms pi bond. Clear? Remember, always when px is there, px is not always sigma bond. Py is not always pi bond. It depends upon which orbitals initially forms sigma bond. Suppose if py forms sigma bond, this becomes pi bond. If px forms sigma bond, this becomes pi bond. Suppose if pz forms sigma bond, these two become pi bond. Like that. Clear? Don't think that always px overlap is sigma, py overlap is pi. That is wrong. Clear? So which of the following molecule have high bond dissociation energy? So which will carry high bond dissociation energy? So first I am writing carbon-carbon double bond, B, carbon-carbon triple bond, C, carbon-carbon this one, and hydrogen-hydrogen single bond. Which molecule have high bond dissociation energy? Answer is B. Why? As number of bonds between two atoms increases, strength increases. Simple. More number of bonds means we need to break more number of bonds. More energy is required. So I can say that triple bond is stronger than double bond. Double bond is stronger than single bond. So here what is hybridization here? sp. And what about here? sp2. And what about here? sp3. So here p character is 50%. Here p character is how much? 33.33. Here p character is 25. Greater the p character, greater the electronegativity. So what is the electronegativity order for hybridizations? Sp is more electronegative than sp2. sp2 is more electronegative than sp3. Greater the electronegativity, greater the withdrawing capacity, greater the acidity. So triple bond is more acidic than double bond is more acidic than single bond. You remember this electronegativity order. Sp is more electronegative than sp2 carbon. sp2 carbon is more electronegative than sp3. Which means if you take the size of triple bond, double bond and single bond. Remember, so this is sp. It is sp. Okay. This is sp2. Size is little increases. Then what about here? It is sp3. Size is more increases. So suppose if I assume that here hydrogen is present outside. So it is connected from here to here, outside hydrogen. So between these two, attractive force is very strong. If I write hydrogen here, attractive force is poor. If I write hydrogen over here, very poor attraction. Right or not? Attractive force is very poor here. Attractive force is strong and here very stronger. So when any carbon having more electronegativity, positive charge is very closer to bond pair of electrons. Positive charge is very close to bond pair of electrons. It can hold that negative charge very easily. So that's why when percentage of S character comes, here it is 50% and what about here? 33.33% and here it is 25%. So what is the relation between acidity and S character? Acidity directly proportional to S character. So what is the meaning of S character? Within the hybridization, what is the percentage of S? Suppose if you assume that S and P both are 100, in that what is the contribution of S? 50%. If you assume that one S orbital, two P orbitals are 100, in that what is the contribution of S? 33.3. Okay. So whichever carbon having more S character, corresponding outer valence electrons of a molecule is very close to nuclei. You remember this point. It is most helpful for most of the acidity questions. Greater the electronegativity, greater the withdrawing capacity. If withdrawing capacity is very high, acidity also very high. Clear? First thing is, try to remove a proton which is very close to nuclei. Is this proton very close to nuclei? Yes, as compared to this one and this one. Suppose the proton is removed here. If this proton is removed from this, here what is the charge you will get? Negative. It is a conjugate base. After removing proton, whatever negative charge comes, that is called conjugate base. Now if I remove this one, here what you will get? Negative. Little mass spectrometry will help over here if you know this. See, between this negative positive, this one and this one, in which case negative is very strongly attracted to positive. First one, why? Very close to nuclei. Is it positive or negative very closer or no? So this negative charge is very strongly attracted by this nuclei. So it can release proton very fastly, you will get stable. See, you are getting negative charge after releasing proton or after gaining proton? After releasing proton. See, in mass spectrometry already explained. See, carbon-carbon triple bond hydrogen is there. So what about these two electrons? If these two electrons, if you add on this carbon, how this triple bond carbon is going to be converted? It is negative, and what about this hydrogen? This is positive. This is called sp carbon. Sp carbon carry negative means you need to imagine like this. Sp carbon having small size, after creating negative charge, then this becomes stable. If this is stable, they never concentrate this H plus, means it is a strong acid. When any molecule after losing proton, if they forms a stable carbanion, then it is a powerful acid. What is this? Conjugate base. If any acid loses proton, forms a negative ion. That negative ion is called conjugate base. If conjugate base is stable, corresponding molecule is a strong acid. If it is unstable, less acidic. Now acidity of any molecule depends on which one? Acidity of any molecule depends on stability of a conjugate base. So that's why this concept is very, very important. So finally, one conclusion between double bond, triple bond and single bond, which is more acidic? Between triple bond, double bond and single bond, which is more acidic? Triple bond is more acidic, simple. Triple bond is more acidic than simple. Acidity solution, see, alkyne. Alkyne is triple bond or not? Alkyne is more acidic than alkene. Alkene is more acidic than alkane. So this I will explain in inductive, mesomeric and hyperconjugation. Right now you remember electronegativity order for carbons. Whichever carbon having more S character, it is a powerful electronegative element or electronegative carbon. Between double bond, triple bond and single bond, which carbon is more electronegative? Which is more electronegative among these three? Sp or sp2 or sp3? Sp carbon. Triple bond is more electronegative. If it is more electronegative, size is very less. Whatever negative charge form on that carbon, that negative charge is stabilized by this positive charge very strongly. That is the reason. This, if you know, acidity of carboxylic acid, acidity of phenol, acidity of alcohol, everything will be very easy for you. Try to revise that mass spectrometry classes. Those who not listen, try to listen from recording video. Still, if you have any doubt, you can ask me after the class. Mass spectrometry I am saying. Because suddenly I will take mass spectrometry class without information. Try to bring that mass spectrometry class notes also. Still I am giving time. Okay. So try to revise that level mass spectrometry classes are already uploaded. That you revise. So roughly I will explain. But in your regular class, I will explain directly the 12th video. So before that, everyone try to revise that level mass spectrometry class, which is already uploaded in your app. Okay, even it is also available in YouTube also. You can go through even that one. But better you try to complete as well as possible. Daytime complete time is there. So you just revise that level videos as well as possible. Don't write first. Don't write. Just listen the class. You take Xerox from your friends, those who are listen here. That is the best idea. Because it will take much more time to write and listen. Every time you need to pause the video and you need to write, it will take much more time. Simply keep aside, keep on watching the video. If any written part is there, that simply ignore it. Try to understand first. That is sufficient. Hardly 2 days is sufficient to listen that level videos. If you listen directly, four videos for 1 day, remaining 4 videos for 1 more day. Only you are listening all the time. Don't write anything. Try to understand. If you pay more attention on that video, single attempt is sufficient to understand the concept. But suppose if you are listening and writing that video, it will take much more time. You won't understood. Okay, my suggestion is try to listen that videos once and twice. Try to complete as well as possible. So next day means 1 day before of starting the 12th video of mass spectrometry, I am going to inform you in your class. On that time, try to write the continuity of that 11th to 12th video in your regular class. Clear? Try to revise as well as possible. In that, if you have any doubts, you can ask me mass spectrometry questions after the class. Clear? See, which of the following overlap is a sigma bond? Which is a sigma bond overlap? Which of the following overlap is sigma bond? Which is sigma bond? This is sigma bond. Yes, it is also sigma bond. It is also sigma bond. All are sigma bonds only. Okay, all are sigma bonds. Every head-on overlap is called sigma bond. All are head-on overlaps or not. Okay, and if you compare the strength, SS sigma bond is very stronger than SP sigma bond, then followed by PP sigma bond. This is the strength of sigma bonds here. SS overlap is very stronger than SP. SP is very stronger than PP. These all are sigma bonds only. But they should be head-on, not side-on. Every S orbital always undergo head-on overlap. But when P orbital is present, there is a possibility of showing head-on and side-on. Clear? It is a sigma bond, it is also sigma bond, it is also sigma. Every negative overlap, head-on overlap. Here PP, it is also sigma. SS overlap is stronger than SP, SP overlap is stronger than PP due to electron density order. Greater the electron density, greater the strength. That is the reason. Which of the following overlap is exist? Which of the following overlap is exist? Minus plus 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 minus minus. All. Which overlap is exist? Which is exist? All are exist. This is sigma bond, and what is this? This is pi bond. See, sidewise overlap. This is head. See, this is head of a p orbital. Here head is overlapping. What is head of s orbital? What is head of a s orbital? S orbital head is which side? Here, in this one. Where is head of s orbital? Take a ball. Take a ball. Where you will stand a ball when you throw on a surface? Where it will stand? Take a ball. I am taking a ball, cricket ball. Throw on a surface, leave on the surface, where it will stand? Where it will stand? All sides are equal or not? All sides are equal means all sides having equal electron density. So all are heads here. Anywhere if they overlap, it is a sigma bond only. Anywhere. It may be this side, left side, below, right, left, any direction. If s orbital overlap in any direction, that is always responsible to give sigma. Okay, but what about p orbital? P orbital, if you observe clearly, this is p orbital, this is minus and this is plus. Over here more electron density is present. When you keep coming from here to here, electron density decreases. This is called node. Node means where probability of electron density 0. There is no electron density here. Here more electron density. If you keep moving from here to here, electron density decreases. After coming here, electron density completely 0. P orbital I am saying. If you are confusing, don't write spherical, dumbbell shape. You write like this. It is plus and this is minus. Okay. So here electron density is very high over here. If you keep on going on, electron density keep decreasing. This is the point where nucleus, probability of finding electron density almost all 0. No electron density here. Finally I can say that here it is a node. Especially it comes in homo-LUMO approach in pericyclic reactions. Here probability of finding electron density is 0. If this is 0, then if you coming from here to here, electron density increases. Here very high electron density. Now from here to here, electron density decreases. Clear? That is p orbital. Is it p orbital having equal electron density in all directions? No. Over here, more electron density. If you keep coming from here to here, electron density, here more electron density is there. Then roughly electron density decreases. Then electron density very less, finally disappears. That is p orbital. So whichever position having more electron density, there if I overlap, that is sigma 1. That's why this is sigma. Here also see head-on overlap sigma. Side-on overlap is called? See, is it head or not? Is it head? Is it a head or not? See, this is one of the orbital, it is a head. Is it head is overlapping? No, head is not overlapping for p orbital. See, this is head. This point is a head. Head is not overlapping. Which is overlapping? Side is overlapping. Sideways overlap. This is sideways overlap. Sideways overlap is weak overlap. Sideways overlap is weak overlap. Head-on overlap is a strong overlap. Both are covalent bonds only. Okay, pi bond is perpendicular to the axis. This is the imaginary axis. This is axis. Along the axis, if overlap takes place, that is sigma bond. Perpendicular to the axis, if any overlap takes place, that is pi bond. Is this overlap is along the axis or perpendicular to the axis? Perpendicular to the axis. Suppose if I take nuclei, this is a nuclei, this is s orbital. This is one more nuclei, s orbital. So now this is overlap and the nuclei. Observe clearly. If nuclei and overlap all are joining on an imaginary axis, that is sigma 1. Where they are overlapping? Over here, right? Now this is a, what is this? One imaginary axis. If any imaginary axis passes through nuclei of two atomic orbitals and overlap, is this axis touching the two nuclei? Is this axis touching the two nuclei or not? Yes. Is it also touching the overlap? Is it axis touching the overlap or not? Yes. Then that's why it is sigma 1. Suppose I am taking a one more p orbital. Here minus plus. Here this is plus minus. Which is nuclei here? This is a nuclei. And here it is a nuclei. Where it is overlapping? Is it overlaps here or not? Two p orbitals. Now join a axis. This is one imaginary axis. Imaginary axis touching the nuclei, touching the overlap, touching the nuclei of second orbital, that is called sigma bond. That is actual definition of a sigma bond. Sigma bond is that one which is lie on a imaginary axis along with the two nuclei. Those are overlapping. Suppose if I take a pi bond. This is a pi bond. Is it pi bond or not? This is plus plus minus minus. So where they are overlapping? Here they are overlapping. This is overlapping. What about these two? Nuclei or not? Suppose if I write an axis along the nuclei, is that overlap is lying on nuclei? No, that is pi bond. Overlap is perpendicular to the axis. But in sigma bond, overlap and nuclei both are parallel to the axis. That is the difference. Clear? How can you define a sigma bond? How can you define a sigma bond? Head-on overlap is called sigma bond, side-on overlap is called pi bond. So during head-on overlap, two atomic orbitals whichever is overlapping, that overlap and their nuclei should lie on the axis. If overlap and nuclei they are not lie on the axis, if they are perpendicular, on that time what you will get? On that time that is pi bond. This is a pi bond definition and this is sigma bond. When two atomic orbitals are overlapping, wherever they are overlap, that overlap and their nuclei should lie on axis. So don't say, sir, I want to write axis like this. Don't, that is not imaginary axis. Imaginary axis should not write in whichever direction you want. Always it should be straight. Clear? Which of the following overlap is non-bonding? Which is a non-bonding overlap? None. Which of the following overlap is non-bonding? Which is a non-bonding overlap? Which is a non-bonding overlap? That is C. This is sigma star. Then what is this? Pi. Same sign overlap in a sidewise pi. If opposite sign is there, pi star. See here plus plus overlap and here plus minus overlap, both are not exist. Plus plus increase the overlap and here it is decrease the overlap. Okay, finally you will get imaginary line. So that is called non-bonding overlap. This is called non-bonding. So three types of molecular orbitals are there: bonding, non-bonding, anti-bonding. This is anti-bonding. So what is the energy order? So this is a imaginary line of atomic orbitals. This is bonding molecular orbitals. What is this? Anti-bonding molecular orbitals, non-bonding molecular orbital. That is the order, energy order. So if you keep writing here, energy of ABMO greater than non-bonding. Non-bonding energy almost all equal to atomic orbital energy. Here I am writing atomic orbitals. This is bonding. Bonding means same sign. Same sign overlap is bonding. Anti-bonding means opposite sign overlap. Non-bonding means you will expect overlap but no use. They will overlap like this. It is not a fruitful overlap. They will come and join and they will leave. But bonding overlap, they will come and they will join like this. That is the difference between bonding and non-bonding. See, the word indicates non-bonding, no bonding. So this will extend the bonding, this will decrease the bonding. That's why you will get imaginary line 0. So what is the d orbital present in dsp2 hybridization? What type of d orbital is present? dz square, dx square minus y square, c dxy, option D, none. Which d orbital is present in dsp2 square planar? Is it square planar or not? sp3 means tetrahedral, dsp2 means square planar. What type of d orbital is present in dsp2? What is the answer? dx square minus y square. Square planar. If it is a tetrahedral, it is not planar. Square planar. Only x and y should be in one plane. You can write in one plane if you take only two axes. Okay? So, If I take dsp2, what is the type of orbital is present? dx square y square. If I take sp3d, you will get dz square. Okay. If I take sp3d2, then dx square y square dz square. Then if I take sp3d3, then dxy dyz dzx, they are the orbitals. Okay. So when any inner orbital comes in overlap 4, see this is overlap 4, sp3, sp3d, here sp2d, inside d means if I use the word planar, square planar, trigonal planar, it should be a diffused orbitals. Suppose if I take tetrahedral, can I use the word planar in that one? No, I am not using planar. Suppose if I take trigonal planar, what is the meaning of trigonal planar? 3 hybrid orbitals are present, they are lying on plane. This is called trigonal planar. Suppose if it is a tetrahedral, this is tetrahedral, above, this side and this side. There is no planarity exist in tetrahedral. Suppose if it is a square planar, this side, this side, this side as well as this side. 4 corners, 4 bonding orbitals are orienting now. So here also the same. dsp2 means dx square y square. Only 2 axes are possible. You can write one x axis and one y axis. So I am suspending a plane, it is bisecting y axis and x axis. Right. The hybridization of carbon in BHC is what is the hybridization of carbon in BHC? What is BHC? Benzene hexachloride. What is the hybridization of carbon in benzene hexachloride? So answer is sp3, not sp2. Okay. So benzene hexachloride, there is no benzene. First you remember, this is called benzene hexachloride. It is the oldest name, still we are applying the same. This is benzene hexachloride, BHC. So famous molecule it is BHC, benzene hexachloride, also called gemaxine. One more name is there, lindane. It is one explosive compound. Many names are there. In the top name is gemaxine. It is not hexachlorobenzene. Hexachlorobenzene is this one. This is called hexachlorobenzene. You write this name. This is hexachlorobenzene. This and this not same. Here what is the hybridization of this carbon? Hybridization of this carbon is sp2. But this is called hexachlorobenzene. Benzene hexachloride. Both are not same. Clear? Benzene hexachloride, 6 chlorines with saturated ring. All chlorines are at equatorial. But in this one, all chlorines are present, they are at planar. Benzene is present in this one. This is called hexachlorobenzene. write that name. Hexachlorobenzene, sp2 hybridization. This and this not same. Our molecule is this one only. Right. Same. The hybridization of carbon in, you write triple bond carbon, in benzene. It is not benzene, benzene is. I will write benzene structure. This is triple bond and this is double bond. This is benzene. So what is the hybridization of these carbons I am asking? sp, sp2, sp3, sp3d. What is the hybridization of carbon present in benzene? sp2. Now I am writing a triple bond and I am saying that the hybridization of triple bond carbon means this one. You can take either this one or two. Okay? So in benzene, it is not benzene. Ene means double bond. Ine means triple bond. It is a reactive intermediate. It is one of the reactive intermediate. Mostly you can expect 1,2 addition reactions. So addition of soda made in liquid ammonia, you will get amination by using this one. Bergman cyclation also possible by using this one. So, what is the answer? Answer is sp2. It is not sp. It is not a real triple bond. Remember, it is not a real triple bond. Only we are writing a imaginary triple bond, but actually it is not a real triple bond. Okay? So in examination, if this triple bond is given, don't think it is a sp. It is not sp. That overlap is a strain overlap. Okay? So especially this molecule, the overlap takes place between these two. See, this is a sp2 orbital and here also sp2 orbital. This sp2 orbital is a sp2 orbital. Sidewise overlap is highly strained. That is not a real overlap. Okay? So these carbons not having any hydrogens and this overlap between these two is not a real overlap. It is a strain overlap. Strain overlap is ready to break. So we can say very easily that it is not a triple bonded overlap. Here one electron, here one more electron is there. That overlap is not a fruitful overlap. Clear? So because what is the angle between these two carbons? 120. sp2 hybridization 120. 120 sidewise overlap is not possible. If they are exactly 0 degree, sidewise overlap is possible. Okay? So that's why this overlap is not exist. It is not a real overlap. It is a strain overlap, highly strained overlap. So whenever if they overlap together intensively, ring become highly strained. It won't survive. That's why this kind of overlaps are not exist clearly. So don't say sp, it is always sp2. So you remember this name, gemaxin lindene. This molecule name is also called benzene hexachloride. In benzene hexachloride there is no benzene, cyclohexane. And what about this? What is the name of this molecule? Hexachlorobenzene. It is hexachlorobenzene. This is benzene hexachloride. Both are not same. It is an explosive compound, highly explosive. It is also called gemaxin, also called lindene. These two are common names. Still this molecule name, still it is survived in IUPAC. Still we are using as benzene hexachloride only. Clear? So that is some examples in hybridization. So in your next class you will see some more additional examples on hybridization regarding the carbon overlaps. Then I will explain how to write hybridization of an inorganic molecule. Okay, so take a break, then sir will continue. 5 minutes break is there. So after that a physical chemistry class will be there. Okay, so every day your timings will be 5 to 8 only. Okay, sometimes we are going to close class in between 8 to 8:30. Officially we are going to announce timings will be 5 to 8:30 or 5 to 8, but class will be closed in between 8 to 8:30. You mentally prepare and come. Okay. So every day we are not going to provide any messages in your WhatsApp group regarding class timings. Okay, sometimes we will mention, sometimes we are not going to mention the class timings. If we are not mention the class timings, your timings are at 5 o'clock only. If we not mention anything. So don't confuse, don't call back to institute number about class timings. If we inform, it's okay, that is not a problem at all. If we are not informed, just remember class timings are 5 to 8 only. That is fixed time. Try to bring your regular notes itself, organic, inorganic, physical. Sometimes faculty, if they don't have any time, proper time is not given on the time. So continuous class will be there up to 3 hours. One faculty will take up to 3 hours. So that's why try to bring your 3 organic, inorganic and physical notes daily. Okay. Mass spectrometry class I won't take suddenly. One day before I am going to inform and I will take the mass spectrometry class. Clear? So your regular organic notes is your GOC notes only. Okay. So occasionally if any time is there and if I want to take any heavy hours, if I want to extend the class, if I want to take 2 classes, by informing you one day before I am going to conduct mass spectrometry class. Okay. Take a break, then sir will continue. 5 minutes break is there. I see.